Hello again.
Hello.
How's it going?
How you doing?
It's all good over here. How's it
Pretty,
going over there?
is it pretty normal over there?
Oh, don't you know it?
It is normal, eh?
Normal day, normal temperature, normal
Normal,
vibes.
normal vibes, right? Maybe we should talk about what then?
Well, shall we talk about some normal distributions?
Maybe, possibly. And it seems that you have some kind of background there.
Yeah, I've got
That's
new
insane.
background, new video. Do this.
There's a square root of a 2 and a pi. Wow, that's cool.
Yeah, we've got some intricacies going on.
Yeah, there's a little bit of, and then e raised to some kind of, what is that? X minus mu, blah, 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 all of that stuff, eh?
Indeed. Well,
Right,
this is the probability mass function. It's not the density function, is it?
I think it's the density function.
Oh,
I think when
you're
we
right.
integrate it, across certain limits, right? From a lower bound to an upper bound, then we'll get an area under there. That'll give us basically the, I think is it the mass function? It basically gives us the probability. Okay.
Oh.
So if I'm understanding, if I'm remembering correctly. So, all right, so let's kind of so there's a lot of different things I imagine that when we measure them, a lot of things may follow a normal distribution, right? Any examples that you might think of?
Well, the reason why it's called the normal distribution is because it occurs so frequently. So there's tons of examples. One just off the top of my head, human error in scientific measurements.
Yeah, hopefully if we're doing it correctly, one of the assumptions is that our residuals should follow a normal distribution. I mean, that was a lot more technical answer than I was asking for.
Okay.
But if I go out and I start measuring something, what do you think might turn out to have a normal distribution?
I don't know.
Maybe,
what do you think?
I don't know, maybe shoe sizes,
Oh,
maybe
sure.
people's heights,
Yeah.
possibly, maybe the weights of dogs.
Yeah.
Possibly, maybe. All right,
Sounds
so
good.
let's see. Let's kind of describe, well, you have the equation behind you, but when people say normal distribution, usually the first thing that should pop into our minds is what?
Is it the bell-shaped curve?
As I think that's right. I think it's this bell-shaped curve. So let me see if I can get a nice axis drawn here. How's that? Straight as an arrow, eh?
Look at that.
Look at that. And what color should we pick for our distribution?
Shall we go with blue?
Blue sounds good to me. Here's the hard part, because this I have to do freehand, okay?
Gosh.
Let's see. So if I have confidence and follow through, I think it should turn out okay. All right. So
I believe in you.
thank you. That's nice. That makes my confidence.
Fantastic.
Not bad, eh?
Mm-hmm.
Not bad. Okay. All right. Let me actually extend that, because I knew that I wasn't going to be able to. Oops. Let me extend that a bit. So there. Okay. So ideally, should be symmetric, right?
Symmetric about the mean.
And symmetric about the mean. I think so too. So let's put in a line here. And we call that, we're going to call that, I think people call that mu, don't they? Mu. Okay, so that's our mean. And if we have some kind of a mean, we'll say mu is the mean. And sigma is the standard. I'm going to not write it all. Deviation. How's that? Standard deviation. How's that?
Nice.
Okay. So basically, okay, so when we say normal curve, immediately we think of a bell-shaped curve, right? Symmetric about the mean. Okay, so everything's happening on the same side of the mean, the same thing's happening, right? And it seems to it peaks at the mean, right? And then it kind of goes down, almost looks like exponentially, right? So it's kind of hovering right above the axis, but it gets closer and closer and closer and closer to it as we move further and further away from the mean. Okay. So I think there's something called the empirical rule.
It's empirical, yeah,
Is it empirical? Okay.
it is.
That if we do have a normal distribution, if I go one standard deviation on each side of the mean, so this would be mu minus sigma, if you can believe that's a mu right there.
That's fine. We know what you mean.
And, and I'm Greek, I should know how to, well, that doesn't mean I have nice handwriting. Mu plus sigma, okay? So whatever the standard deviation is, whatever the mean is, if it follows a normal distribution, I can expect, I'm going to quiz you right now, okay? All right. Is that okay? I'm going to put you on the spot, but I have total confidence in you.
I'm ready.
I do. All right, so here, between one sigma away from the mean on each side. Oops, let me fix that. Okay. What percentage lies between those two bits?
That is a total of approximately 68%.
That's awesome. That's right. So from here, so that's 68%. The middle 68 is what we would expect between one standard deviation above and below the mean. Beautiful. What if I go out here to try to keep the color coding going on here?
Well, before you just move on, just a sec, because of the symmetric properties of the normal distribution, we can expect 34% in each of those. So between mu minus sigma and then mu and mu plus sigma.
That's exactly right. That's exactly right. Because of its symmetry, whatever's on the one side of the means happens to be the same on the other side. So if I go out the same distance away, in this case, one standard deviation, you know, that if that collectively 68, then half of it from the mean to any one of those is going to be the 34%. It's exactly right. It's exactly right. All right. How about mu? See that? See that? I tell you what, when we have confidence in ourselves, sometimes that's called delusional, but I don't think in this case, right? I think
not today.
I think not today, not with this. Okay. Now, if I start saying that I'm an excellent dancer, now that I would say is delusional. So
I'll take your word
not
for
as
it.
much confidence on the dance floor as talking about the normal distribution. Mu plus 2 sigma. All right. So now between these two, I'm going to use again a different color here. Let's try orange. Between here, you get the point right there. And here is what percentage?
So that's going to be a total of 95%.
That's right. Look, we even have arrows here. 95% is exactly right. So when we're trying to set up 95% confidence intervals, right, they cover the middle 95%, we almost can go out to, we go out to 2 standard deviations away for the normal distribution. So yeah, this would be 95%. And I think specifically for exactly 95, it's not exactly 2. It's more like 1.96, something like that. I think it's 1.96. So about 2 standard deviations away. That should give you the middle 95. Perfect. And then finally, we go out to, we'll use pink now, mu minus 3 of those sigmas and mu plus 3 of those sigmas. And between those two, how much is this?
Now, this is where I have to look at my notes here because I forgot off the top of my head. It is approximately 99.7.
That's exactly right, 99.7. Now, that's only 3 numbers to remember.
I should do better. I've disappointed you, George. I'm so sorry.
I'm joking, man. I'm joking.
I mean, you say you are, but I know you.
Yeah, well, I'm gonna call. I'm gonna wait till you're in front of a bunch of people and ask you the same question. You're gonna stand up proudly and say 99.7%, right?
There we go.
0.7. All right, that's right. So almost pretty much 100%, close to 100% is within 3 standard deviations of the mean when we're talking about a normal distribution. Right. Great. So, and if we wanted to be able to figure out what it is specifically, we can always use what's. Do you think? It's
Are
nice.
you,
Go ahead.
are you referring to the normal table?
Yeah, absolutely. I mean, there's functions within our Studio or Excel that will give us exactly the values. But lots of times, especially if we're taking a test and you're not allowed to have a lot of extra technology with you, they'll give you a particular, how do you call it? They'll give you a table, and then you have to be able to learn how to read that table to figure out what the values are, you know, how far away I have to go from the mean to enclose a specific probability, a specific area under that curve to get a particular probability. Okay. But I'm going to ask this, okay? Out there is a bunch of different measurements that we take that have all kinds of means and all kinds of standard deviations. Look at that, eh? How's that for graphics?
Nice.
Nice, huh? So not everything's going to have the same mean. Not everything's going to have the same standard deviation. So I might want to do what with those numbers if I'm asking the probability, let's say, if I ask the question, the probability, if I tell you that the mean mass of a dog is 20 kilograms, and I tell you the standard deviation for the mass of the dogs is, let's say, I don't know, 5 kilograms, and I'm just, you know, yanking these out of the air. How am I to kind of use this and use a normal distributions to figure out what the probability might be of some dog chosen at random? Let's say some dog chosen at random that their mass, let's say, is greater than if I said, let's say 25. Now here, we may not need a table. Why do we not need a table?
Well, we can just use the graph here because mu is 20, sigma is 5, and 25 is mu plus sigma.
Right. So this would be 20 right here. This would be the 25. Right. So if I'm asking what the probability of X being greater than that is, I think I'm looking at this, aren't I?
Yes, exactly.
And because we know that this bit is, here, I'm going to use different color. We know that this bit right here, oh, that's terrible, but you get the point. That bit right there is how much?
That was 34.
34. How much is from here all the way out to positive infinity, I guess?
Well, that would be 50%.
That's exactly right. Because of the symmetry, everything, the stuff that's above the mean is 50%. The stuff that's below the mean represents the bottom 50%, right? So I've got 50%. So what's this going to be? I'm going not going to talk you through it because I know that you know exactly what this blue bit's going to be.
So that is simply 50% minus 34%. That's going to give us 16.
50% minus 34%. That's going to give us the 16%, isn't it? So yeah, so we were able to answer this question, not necessarily looking at a normal distribution or a standard normal. Standard normal. So when we're dealing with normal distributions, maybe, you know, if I asked for, let's say, the probability of some dog chosen at random is greater than, let's say, 27. Now all of a sudden I'm not a full certain amount of standard deviations away, am I?
No,
so
that's going to be harder.
We're kind of stuck, aren't we? Right. So now we actually have to take these values, right, take the value that we're interested in and also kind of incorporate our mean and our standard deviation so that we can be able to use a standard normal table. So a standard normal table, right? We can talk about the probability of X being, let's say in this case, greater. Sorry, did I say greater than? I said greater than, didn't I? Yeah. Greater than 27, okay? Or in general, if I say the probability of our random variable X, that's capital X, is greater than some given value, I'm going to call lowercase x. So lowercase x is actually a fixed value. Lowercase x for us is 27 in this case, okay? I could say, well, you know what? I don't have a table that's got a mean of 20 and a standard deviation of 5, but the standard normal has a mean of 0 and a standard deviation of, tell me, what do you think?
I don't know. Would it be X?
Not X.
Not X.
When we standardize it, basically what we're doing is we're finding a Z value, okay, by taking our value that we're interested in, subtracting the mean, and then dividing by the standard deviation.
Of course.
Okay, so after we've standardized it, our mean becomes 0 for a standard normal distribution, and our standard deviation becomes 1. So when we look at a standard normal table, which we'll probably see, let me make this a little smaller. When there's really small print, it's tough to, oh, you can see my issue here. Hold on.
Oh, technical difficulties. There we go.
There we go. Okay, there we are. Didn't want to stretch it. When we look at our standard normal, okay, it's still a bell-shaped curve, but now it's centered at 0. And by the time I go out to 1 and -1, right, that represents 1 standard deviation away from the mean. So this is on a standard normal. I can expect that the area that's between -1 and 1, in this case, -1 and 1 represent 1 standard deviation away from the mean, which is 0. Let me make sure that looks like a 0 here, right? This is that 68% we were talking about. So if we want to use the standard normal table, we have to find a Z value. Because the Z value, when you see a Z value, that's a hint that you're using the standard normal. So when we take our X value that we're interested in, right? Let's use our own values, right? Well, we used what before? We asked the probability of X being greater than 25. That was the first one we asked, and we ended up getting that, whatever it was, at 16%, right? We say that this is exactly the same as the probability that our Z value, which is the standard normal, so here the mean is 0, the standard deviation is 1, is greater than whatever X value I'm interested in, which is 25. I subtract it from the mean, which in our case was 20, I believe, right? And we divide it by our standard deviation, which was 5. We end up getting a probability of Z being greater than, looks like 5 divided by 5, 1. So didn't that give us this bit right here?
It certainly did.
So what it did was, by subtracting the X value that we were interested in, 25 in this case, by subtracting it from the mean, we've taken our distribution and moved it so it's centered above 0, right? And then when we divide by our standard deviation, we're scaling it. We're scaling it so that a standard deviation actually becomes 1 when we're looking at the standard normal. So when we looked at our line which had 20 here, 25 here, isn't 25 5 units on this side of 20? How
I'd say
many
so.
units? How many units of 5 is
That'd be 1 unit.
from 20 to 25?
It would be 1 unit of 5.
It's 1, isn't it? So in our case, when we want to figure out what the probability is of being greater than 27, that means that it's a little bit more than 1 standard deviation away, isn't it?
Mm.
So let me see if I can make this a bit smaller. Wow, I'm gonna do, I think this reminds me of like I don't know, something to do with fractals. No, not this. Oh, geez, I look at that. That was terrible. Look at
Not
that.
to worry.
Oh God, you know what? Always worse. I think Control Z. Control
There we
Z
go.
saved us again. Okay.
Okay.
Let me just go to a different. Let me go to a different. How do you call it?
Different page.
A different page. Thanks. I forgot what I was going to do. Oh yeah. Okay. So we were going to ask now what the probability was of X being greater than 27. Well, again, with our mean still equaling 20 and our standard deviation equaling 5, right?
Mm-hmm.
That's the same as the probability of our Z statistic, our Z value off the standard normal being greater than, here's the 27, 27. That was the value of X we were interested in, minus the 20, which is the mean, divided by 5, which is the standard deviation. I think we end up with a probability that our Z statistic is greater than, what is that, 7 over 5?
1.4 or something.
1.4, exactly
Yeah.
right. So 1.4 standard deviations away. So now, if we look at a standard normal table, we'd be looking, here's 0, the mean is 0. Here's our Z value that we ended up with at 1.4. We're looking for this area right here, aren't we?
Oh.
Right? So I think we might want to use a table in this particular case.
I think that might make our lives a bit easier.
Yeah, it's going to make our lives a lot easier. You know what make it even easier is using Excel or RStudio to figure it out, but we'll go with this. We'll go with the table because that's kind of what a lot of people have to use. All right, so let me see if I can pull a table up here, a nice one from Google. So I'm going to type in standard normal distribution table, the first option after 3 letters. I wonder why. Images, please. Oh, well, let's see. Maybe this one's nice. Let's see if that comes up nice. If it does, I'll share it. If not, I'll find a better one. Taking forever. I don't know who's, what the hell is this? That one. Hypothesis. All right, here we go. I'm going to use this.
Okay.
This one right here. Let me share that.
You're sort of fading in and out.
Am I fading in and out a little bit?
You're freezing every now and then.
Okay. All right. I'm going to try my best not to freeze from this point out. Okay. Do my best. I'll do my best. Okay. Sometimes our internet isn't working as nicely as we wanted to. Let's try this. There we go. All right. Do you see it? Hopefully coming up here at some point.
There we go.
All right, cool. What does that say? Freakonometrics.
Freakonometrics. Okay.
I don't know what that is. We like to thank whoever created this site that we're kind of using here. Let me make a reference to it. Hypothesis, it says here, generating your own normal distribution table. Okay, that's fair. Wow, that's kind of cool. But I believe this is the standard. Can we see these numbers up here easily?
I can see it if I lean in a bit. I think it'll be fine.
You think it'll be okay? All right,
Yeah.
okay. So when the first thing we do to be able to figure out, okay, how to use this particular table is we need to look at the legend.
Okay.
And when we look at the legend, it shows us the shaded bits. That's the bits that we're going to see in the body of the table. Okay, so those are the areas. But notice that this one starts at 0, 0. Okay, and notice for 0.0 and at the top 0.00. So basically, that's giving us a z value of 0. What's the probability associated with that? You see it? This may
Indeed, that's 0.5000.
Yeah, that's right. That's exactly right. So that's 50%. So what it's saying is like when you start at 0, the stuff that's to the left of it is 50%. So why are they only giving us positive z values?
Good question.
What do you think? Why? I think you answered this question before.
Is it because we're starting at the left-hand side of the curve and we're moving towards the right?
We're starting at the left, moving towards the right. But it's not showing those negative z values because if you see here, I don't know if you can see it, right here is 0. So it's not representing any of these values.
Okay.
But right when it gets to 0, it says 50%. Right? So the reason they don't show the negatives is because the normal distribution is
I know what you mean. Symmetric.
the metric is exactly right.
There
Yeah,
we go.
they would just be repeating the same information. So we can get everything we need from this particular table. Because sometimes you'll see, in fact, sometimes you'll see a version of this, but with the negative values, and then you'll see the red, the legend part, kind of start behind 0, the negatives. So it'll give negative z values along the vertical and the top, along the vertical margin. The vertical and the horizontal margin up top. Those are actual z values. So as we're moving along, it's letting us know what the cumulative values are. And we can use symmetry to be able to figure out, possibly in this particular case, because we're looking to find what value of z were we interested in. Do you remember?
1.4, wasn't it?
1.4 is exactly right. So when I look at 1.4, right? And then here are the hundredths digits up here, okay? That's tough to say. So we were looking at exactly 1.4. If it was 1.45, I would go to the 1.4 and then come all the way out to the 0.05 column, which is this one, I believe. So it's giving us that increment in the z value of 100th as we're moving this way. Okay, so what is that value? I can't hardly see it. Let me put on my glasses.
Your mouse is covering it, I think.
Oh, is my I'm sorry.
Not to worry.
Glasses. All right, back again.
Got them? Fantastic.
1.4, I get points. 9192.
Yeah, I think so.
That's look right. Okay, so 0.9192. So that's the area from negative infinity all the way up to 1.4. So what are we going to do?
We're going to have to do 1 minus that because we want the opposite.
Because we need that bit that's up that way, right? Exactly. Beautiful, beautiful work. All right, so you're going to help me now and tell me what that equals, if that's okay.
0.0018.
0.00.
Oh no, that can't be right. Hang on. 0.0818.
Yes. I think that's right. I think that's right. All right, cool. So let's write that down.
Sure. Not good to make silly mistakes like that.
Oh, that's okay. That's okay. Hey, all the greats make some mistakes every once in a while, okay? All right.
Thank you.
And if for nothing else, just to make everybody else feel comfortable that even somebody as great as you makes a mistake, okay? So
thank you.
Very diplomatic, okay? So let's say, so we said 1.4. So this area here we said was 0.9182. Is
Mhm.
that right? So that means that this bit has to be 1 minus that 0.9182. I hope I didn't. Yeah,
I think that was right.
0.9182.
Yeah,
So we said that was 0.0818. Is that right?
I think so.
All right.
Oh, that was what we said, wasn't it?
I think so. I
Cool.
think that's correct. All right, so there, we're able to use any, if it's normally distributed and we know what the mean and the standard deviation are, we're
Mhm.
able to figure out specifically, we were able to standardize it, right? Using the Z score, which is equal, my connection's a little bit slow. Am I choppy?
A little bit,
Was
but
I
it's
choppy
okay.
there? It said that out, it said your internet is unstable.
Ah,
That's what it said.
we'll have to end this soon then.
Okay, well, at least, at least, at least it wasn't saying that I'm unstable. So it's just the internet that's unstable here.
In the sake.
Okay, so that's our X value minus our mean, which centers it at 0, and then divided by sigma, which shapes it so that the standard deviation is going to be 1. As soon as we're able to standardize it, we're able to go straight to the Z table, to our standard normal table, and figure out for a certain Z value, what's the probability associated with that. That's not bad for a video for about
It's
normal
not bad.
distribution.
So before we finish though, we're going to have to tie our answer back to the question because we can't leave it like that.
Oh, right. We have to finish the whole story, don't we?
So we were saying, what was the probability that these dogs have a weight of over 27 kilograms? So, I mean, I personally like to work in percentages. So I would say that would be 8.18%.
If you insist. Well done. That's exactly right. We've just answered that particular question. It's
Yes.
got to be, go ahead.
Oh, no, I was just saying nice.
Right? Because when we were at 1, right, what was above 25, we knew that that was about 16 point blah, 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 something like that. So going out a little bit further, that gets us down to the 8.18, right?
Exactly.
Oh, pardon me. Sorry about that. All right. So, and if you look at it, that crazy business over there, we might as well just do one more thing before we go, if that's okay.
Sure.
Because we've got the probability, right? Or it's a probability mass function. I think they just say f of x, maybe they call it. And that's the mass function. Sorry, not the mass function, the density function. It's basically talking about this curve right here.
Okay.
So if that's equal to 1 over sigma times the square root of 2 pi e raised to the, that's beautiful, e raised to the open parenthesis x minus mu, I think that bit is squared. That's kind
I
of
think it might
off.
be. It's off, isn't it?
Possibly divided by 2 sigma squared. So this bit right here is the exponential, sorry, is the exponent on our e. Now, why would it get a max here at 0?
Because it's negative.
Go ahead.
Sorry, just because it's negative?
Because this bit right here, we're raising e, which is a positive value. We're raising it to a negative value, right? All of this stuff in here, let me use another color. Oh, I like lavender here. All this stuff in here, right? The sigma squared, the x minus mu collectively squared, the 2 itself, that's all positive. As soon as I throw a negative on it, I'm raising e to a number that's either 0 or negative. So the biggest that's going to be is when I raise e to the 0, right? Because anything else is going to give us smaller numbers, either the -1, either the -2. That's just 1 over e to the 1 or 1 over e to the 2. So that's a number in the denominator that's getting bigger when we have a negative exponent, right? So it makes sense that it would peak right where x equals mu. So when that equals 0, that's how we get a peak right at the mean mu, or if we standardize it, we get a peak at 0 because mu becomes the mean after you standardize it.
Yes.
Right on, man. But what's weird is that this 2 pi business is in there, ain't it? To hell, I don't know. Maybe we'll leave that as an exercise for anybody
Gosh.
watching the video to kind of let us know.
Let's see if anyone can prove that. Can they send it in to us?
Send it in to us, and then, you know, we'll pretend we thought of it. No, we don't do that, right? We don't do
Pretend
that.
we imagine the
We're
proof.
ethical, right? We take credit for our own stuff, and we give credit to other people that do stuff. So I give credit to you
Thank you.
for that awesome awesome session about normal. You ever hear about the Shapiro-Wilks test? I got a little joke for you. You ever hear of the Shapiro-Wilks test?
I have heard of, yes.
Okay, so that is you take a particular set of data and you're checking to see if it's normal. So then if it has to be normal, that's one of the conditions that has to be satisfied in order to do some type of analysis, maybe linear regression or something else, maybe a t-test, when you're trying to test between means or something. So here's the joke. What is it? How does it go again? I think I should perform the Shapiro-Wilks test on myself because I don't think I'm normal. No, terrible, huh?
Dreadful.
Well, pitiful.
I'm sorry.
Now, hey, no, you have to be honest. All right, we'll edit that bit out, okay? My last joke. Oh,
Wow.
not normal. I've done the Shapiro-Wilks test on myself and I found out I'm not normal. That's not funny. The delivery, I'll work on the delivery a little bit more. Okay, I won't announce that it's a joke before I say it.
Sure.
That kind of kills it a little bit. All right, so all right, Laura, is that enough for normal distributions?
Yeah, I think that's enough for now. If we have any more to say, then we can do a part 2.
We'll be back. We'll be back again, right?
Fantastic.
All right, kiddo. Well, you have a great rest of your day, and
Thanks, you
I'll
too.
see you in the next video, okay?
Great. All right.
Bye, everybody.
Bye.